decomposition or SVD. And we last lecture we looked at 3 applications of it. Yeah, one to image compression, one to visualizing a data set, one to we wanted to find this axis of the spiral galaxy, right? And I mean all the 3 was done using the same approach. Yeah, we made use of some fact about SVD. Do you remember what that fact is?
We can write as sum of or outer product of the eigenvectors.
Yes, but not just that. Yeah, something more we used.
The eigenvalues are sorted, so we can approximate it by taking the first few.
Yeah. So if you take the first few eigenvectors, what do you get?
An approximation of the whole data set.
So not just an approximation.
We can ignore the other eigenvectors to simplify calculations.
Yeah. In fact, you will get what is called the best fit subspace. Yeah. And today we will be proving that proof that you wanted to know, like, why does this work? Yeah. So you were asking for a proof, and we will do that proof. Yeah? So let's begin with what SVD is. Yeah. So let's say you have some points. Yeah, you have n points x1 to xn in d-dimensional space. Yeah, and let's write this set of points as a matrix. Yeah, so typically the number of points is much larger than the dimension. So things will look like this. Yeah, so just a second. Do I want everything to be a row or a column? Yeah, yeah. I think everything I want it to be a row. So each of these x's is a row. Yeah, so this is n dimensions here, and this is d dimensions here. Yeah, and what can we say about M? So what does SVD say about M? Let R be the rank of M. Okay. So what does SVD say about M? Yeah. No ideas?
So we can represent it as U sigma V transpose.
Yeah. So U sigma V transpose. That's all?
So sigma has the R terms 0 to 1.
Yeah, so you can write this as a summation of simple matrices. Yeah. You will have R matrices, and what is the R matrices? What are the R matrices?
Also root mi.
Okay.
So VI UI transpose.
Yeah, it's VI UI transpose. I will write it slightly differently. Okay, I will write it as WI VI transpose. Okay, and where? Yeah, so these eigenvalues are stored. Yeah, so this lambda 1 is greater than or equal to lambda 2 greater than or equal to lambda 3 up to greater than or equal to lambda r. Yeah, and then rest are okay. That's all, and this is greater than 0. Yeah. So these are some numbers. Yeah. And what are so and VI's are orthonormal eigenvectors, yeah, of M transpose M. Yeah. So this is a matrix. What's the dimension of this matrix? What is the dimension of this matrix?
D cross D.
D cross D. Yeah, with eigen value lambda I. And what are WI's? What are W is? So this Vi belongs to R raised to D, okay? It's a D-dimensional vector. And Wi belongs to R raised to
N.
Yeah, N. And what is Wi? How can we write
N.
Wi?
M transpose, the orthonormal eigenvectors of that.
Yeah. So you will get this as M times Vi divided by square root of lambda I.
Yes, sir.
And this also happened to be orthonormal eigenvectors of M transpose. Okay. Yeah, I mean, it's maybe I previously stated it in the slightly different way. This is the same thing only. I think everything I did a transpose or something like that. Okay. Okay, so this was the statement of SVD. Yeah. Okay, and what was our claim last time? So we proved, showed a lot of practical results. What was our claim? Yeah, what was our claim? How did we find the axis of the galaxy? What did we show?
We
The
took the
projection of M on the eigenvector of the largest eigenvalue.
Yes. Yeah. So we showed that span of V1. You take the dimension, vector space spanned by V1. This is the best fit one-dimensional subspace or a line through origin. Okay. Yeah. When the span of E1 is the best fit one-dimensional subspace. Yeah. And more generally, what we stated was the span of V1 to Vk. Yeah, is best fit k-dimensional subspace. Yeah. So what does this mean? In 3D, yeah. So let's start with 2D so that this we understand first. Yeah. So let's say there are a lot of points. Yeah. And the best fit line is some line like this. Yeah. And if you look at the projection of these points, that this distance. So these points are x's. Yeah. So these points are x1, x2, x3, x4, x5. Yeah. And let's call this perpendicular distance a1, a2, a3, a4, a5. Yeah. So yeah, what do you mean by best fit one-dimensional subspace? What do you think it means?
That line itself.
That line
Such,
itself.
such that A1, A2, A3, all those A's are minimal.
Yeah.
So the sum of their squares are minimal.
Yeah. So best fit means summation over I equal to 1 to n ai squared is minimized. Yeah.
Sir, wasn't it absolute value of AI?
Absolute value of ai. Sum of squares of perpendicular distance is what we are minimizing. Yeah. Yeah, ai squared is a positive number, so it's like yeah, same as yeah, absolute value of ai in some sense. Okay. Yeah. Okay. So what do you mean by best fit k-dimensional subspace? So this is for a line, no?
Yes, sir.
So what is the best fit k-dimensional subspace?
For which dimensions is the so if we take it in a 3D space, along which plane will the square of perpendicular distance be minimized?
Okay.
Along.
Yeah. Okay. Yeah. So let's write it slightly differently. Yeah. So let's draw something. So let's say I draw this particular line. What is the length of this particular line?
X1 square.
Norm of x1.
Yeah, just norm of x1. Yeah. Can you tell me the length of this particular thing?
It's the norm of x1 square minus a1 square whole root.
But this particular thing has some. There is another simple expression for this.
The norm of the projection.
Yeah. So let's let the unit vector along this direction be v hat. Okay, this is the unit vector along this direction. So what is this distance?
X1 dot v hat.
So it is x1 dot v hat. Is that clear? Yeah, is that clear to everyone? It's a projection.
Yes, sir.
So from this we can write an equation. Yeah, what can we write by Pythagoras?
a1 square plus x1 dot v hat squared is equal to norm of x1 square.
So this thing we can write it as, yeah, instead of ai squared I can write as summation over xi squared minus xi dot v hat squared. Everybody agrees?
Yes, sir.
Yeah. Yeah. So I mean v hat. So best fit means find the direction v hat such that this particular thing is minimized. Yeah. Yeah. So can we say something in terms? Yeah. So remember we learned the argmax thing, no? So what is argmax? Can we write this in terms of argmax?
Argmax or argmin, sir?
Yeah, argmin. Sorry, argmin.
Then argmin of this whole expression.
Yeah. So v hat, let v hat be the argmin. Yeah. Over let's say, so we want unit vectors. Yeah. Over vectors with norm equal to 1. Yeah. Summation over I equal to 1 to n norm xi squared minus xi dot v the whole squared. Is this clear to everyone what this means?
Yes, sir.
Yes, sir.
Anybody has a doubt what this statement means?
So shouldn't we also give the restriction that D here has to be a unit vector?
Yeah. So that's why I have written
Okay. Yeah.
this here. Yeah. Okay. Yeah. Now you look at this and the span of v hat is essentially our best fit line. You agree?
Yes, sir.
Yeah. And what is our claim? What is our claim? I mean,
So the sum of a1's all ai squares is minimized.
no. Our claim is v hat is equal to v1. Yeah.
Yes.
Our claim is this v hat is actually equal to the v1 sitting here. Yeah. That's what we want to show. You agree?
Oh,
Yes, sir.
Yeah. Okay. Right. Now you look at this expression. Yeah. You can do some manipulations. No. What can you say about this expression?
You know the first part,
We
xi
can-
square is constant, so you can take that out and just maximize the squares of the dot products.
Yeah.
So
So this part does not depend upon VIs at all. That's what you are saying.
Yes, sir.
Yeah, that's what Vidit is saying. Yeah, Vidit is saying, okay, look, this doesn't depend upon VI. So yeah, why is this sitting in our argument? Yeah, so you can just write this as argmax of norm V equal to 1 summation over I equal to 1 to n xi dot V, the whole squared. So far so good?
Sir, argmin, yes?
No, there's a negative sitting here, no? Yeah, the way to maximize this is minimize this.
So why are we considering it through origin only?
Yeah, so it's a subspace. Yeah, so okay, we are considering through origin only. Yeah, so if we want to if you want to do a SVD of a general set of points, typically what you do is first you change the origin to basically the mean of the points. Okay, and then you will apply SVD. So the best fit subspace will always pass through the origin. Yeah, so right now we are only talking about best fit subspace, and subspace will pass through origin. Yeah, to have the zero vector in it.
Yes. Okay, sir.
Yeah. Okay. Yeah. So now, yeah. So this is a weird thing, right? This is a weird thing. Why should this be equal to V1? Why should any ideas? Yeah. Yeah. Let me ask a slightly different question. Yeah. So can we say write this slightly differently? Yeah. What I mean is, so what is x's? X's are rows of the matrix, right? X's are rows of the matrix.
yes, sir.
This is the matrix. These are the x's. Yeah. Yeah. And what if I multiply this matrix by the vector v? What will I get? So what will be the entry here?
So
Xi dot V.
Yeah, so this will be x1 dot v and xn dot v. Okay. Now, yeah, is there a nicer way of writing this?
MVI.
Yeah. Everybody agrees, disagrees?
No, sir, I don't think it should be MPI.
So what is this quantity? Yeah, in terms of this.
It is the sum of the squares of the coordinates.
Yeah. So sum of the squares of the coordinates
It is
of
its
MV.
sorry.
Yeah.
Like
It is the
transpose
norm
it.
squared of that. You agree?
Yes, sir.
Yes, sir.
Okay. Yeah, and yeah. Okay. Now we somehow want to relate this, yeah, to the eigenvectors of M transpose M. We want to relate this to the eigenvectors of M transpose M. Yeah. So what should we do? What should we do? We want to relate this to the eigenvectors of M transpose M. Nobody want to attempt?
I believe you could write it as a dot product,
V
you write
norm
these-
is 1, sir. So maybe something
What?
along that line.
Vidit was saying something. Sorry,
I
what is
think
that?
I believe I'm not sure, but I think you write the norm square as V transpose V. So you can write this as the transpose of MV into MV.
Okay, very nice. Very nice. Okay, and then what will you get?
then you apply the transpose, you get V transpose MT into MV.
Okay. This
I'm
will
not sure what to
become
do after that.
V transpose M transpose M V, and V was the eigenvector of
M transpose M.
so V1 was the eigenvector of M transpose M. Yeah. Yeah. So this is a symmetric matrix, no? This is a symmetric matrix. You agree?
Yes, sir.
Yes, sir.
So we can do the spectral decomposition.
Yes, sir.
So what does that give you? There is some V transpose sitting here. There is spectral decomposition will go in here, and V you will get here. So what is a spectral decomposition? What is the spectral decomposition of M transpose M? What are the eigenvalues and eigenvectors of orthonormal eigenvectors of M transpose M?
Lambda I, lambda M, Vi.
Okay. Jatin was speaking.
Yes, sir. The eigenvalues are from lambda I to lambda R, and the eigenvectors are from Vi to V1 to Vi. So
Yeah.
that
So
will
what?
be a part of summation.
Yeah. So how should I write that?
Lambda I,
Lambda I, Vi, V transpose.
Vi, V transpose.
Nice. Okay. Now what should I do? What is this thing?
So we know that lambda i's are in decreasing order. So lambda 1 will be the maximum of these. Maybe that is something we can use to prove that this argmax will be V1. I'm not sure.
Yeah, look closely. You can see more interesting things. What is sitting? Like, let's say you open out the bracket. What will you get?
Can you take like the V transpose and the V inside?
So you can take this inside, and there's what will you get?
So you get
We get
the
V
dot product squared.
Yeah, we get V transpose whole transpose. And then that is multiplied by V transpose V. So we get a dot product.
Yeah.
So we bracket V transpose V together. Yeah.
Everybody agrees about this?
Yes, sir.
Yeah. So when is this quantity maximized? Now that's our problem. When is this quantity maximized? For what value of V?
Vi is equal to V because both of them are orthonormal, so maximum value is 1. So both of them
this last step
have to be equal.
Okay, somebody had a question about last step. Aditya?
Yes, sir, but we can define inner product in any arbitrary fashion, right? Why are the... So I didn't get how you got the last step.
Here the inner product is dot product only. So Vi dot V is, yeah, I am defining the inner product as a dot product only. Sorry, that was the confusion.
So, but in general, how can we consider that? Shouldn't we consider any inner product?
Yeah, so currently our inner product is the dot product. Yeah, just assume that. Yeah. I'm not stating anything with respect to general inner products. I'm just stating anything with respect to dot product only. Yeah. So the thing is, it's easy to miss business dot product, just dot everywhere. So it's better to write things like this. That's why I'm writing that. Okay.
Yes, sir. Thank you.
Okay. So yeah. Now a question is, when is this maximized? Yeah, when do you think this is maximized?
Vi is equal to V. Sorry, V is equal to, yeah. V is
Which
equal
Vi?
to V.
So there are n Vi's. How can all of them be
Sorry,
equal
sir.
to V?
The first Vi.
First one, because it's in descending order.
Why? I don't know. Why should only be? Jatin had
So-
something to say.
Sir, I'm not sure, but we had the non-increasing order of eigenvalues, and
Okay.
we want to maximize vi comma v.
Mhm.
So v1 should give the maximum, I guess, but I'm not sure.
So vi comma v is only going to be one or less than equal to 1.
So why can't I take a linear combination of v1 and v2? Then also you can do better, no?
But v1 cannot be equal to both v1 and v2, can it?
Yeah, it can be
Depends on
v1
their
plus
extent.
v2. v1 plus v2.
Sir, I didn't understand what you're saying about the linear combinations.
So our question now is, when is this maximized, right? And yeah, somebody is saying when v equal to v1, this is maximized. Yeah. So my counter argument is, let's take v equal to v1 plus v2. You are getting even better, no? You are getting lambda 1 plus lambda 2.
But the magnitude has to be 1 only, no sir. So it will be decreasing, like you'll get by root 2 or something.
So yeah, so the thing is, the norm has to be equal to 1. Okay. Yeah. So if norm has to be equal to 1, the norm of v equal to 1 implies, so what is this thing? What are these vi dot v? What is these quantities?
Projection on the eigenvectors.
Yeah, they are the coordinates with respect to the eigenvector basis. They are orthonormal eigenvectors, right?
Yes.
Yeah.
Yes, sir.
So this implies that this summation over I, yeah, this vi dot v, this whole square is equal to 1. You agree?
Yes, sir.
Yeah. Now this summation has to be equal to 1. Yeah. This summation is slightly different because you are multiplying things by lambda I. Now you have this restriction and you want to maximize this summation. When is that possible?
So when we maximize the largest term of the sum.
Yes, you need to maximize the largest, the term corresponding to the largest lambda I you have to maximize. That's the only way to maximize this sum and make that equal to 1 in fact, right?
Yes, sir.
Sir, it doesn't seem very non-trivial for me. Like how does maximizing the largest term maximize the entire sum?
Yeah. So you need to make this argument, then only you can say. You need to use this, otherwise, yeah, if you understand this, then you will find that the argmax is actually v1, yeah, with value lambda 1. Is that clear to everyone?
Sir, just one doubt. So when you said like that linear combination thing, when we could have made it v1 plus v2, if we divided v by root 2 in order to make it like
For root 2, sure.
Yeah, so the v is normalized. How can we guarantee that in that case the sum
in that
would
case,
be
what
v1?
is the summation? In that case, what is the summation?
Sir, it will be some x quantities of lambda 1 and 1 minus x
What is
quantities
that
of
x?
lambda 2.
X is 1
is
by 2.
smaller
No?
than 1. X is, yes, sir. In this case, it is specifically 1 by 2. But for any linear combination, x will be some value which is less than 1.
Yeah.
And we'll add the other part with lambda 2, and it will always be less than lambda 1.
Yeah.
So it directly follows from lambda 2 less than lambda 1.
Yeah.
Okay.
So is that clear?
Yes, sir.
Yeah.
So I had another doubt. Sorry.
Yeah,
What if lambda 1 is equal to lambda 2?
Yeah, lambda 1 equal to lambda 2, then there are multiple choices. I agree.
Okay.
Yeah, but v1 is one of the choice. You agree?
Yes, sir.
So this v1 is not unique. I completely agree with you. Yeah, but if the eigenvalues are distinct, then it's unique. You agree there?
Yes, sir. Got it, sir. Thank you.
Okay. Perfect. Okay, so what have we done? What have we showed? What have we showed?
Sir, could you please explain how we showed that V cannot be a linear combination of V1 to Vn? Like, how is it V1?
So you agree that if the norm of V equal to 1, sum of squares of dot products of Vi with V is equal to 1?
Yes.
Yeah. Now, suppose V is some linear combination of V1 and V2. This is what was suggested. Let's say it is V1 plus V2 by 2. Yeah. Suppose V equal to V1 plus V2 by root 2 because it has to be a unit vector. Okay.
So this may not. Okay, this is a root vector. Okay, this is a unit vector.
This is a unit vector. Now, if I substitute things here, I will get lambda 1 by 2 plus lambda 2 by 2. Do you agree?
Yes.
Yeah. And this is less than lambda 1. Do you agree?
Yes.
Yeah. So what is happening? These quantities form a probability distribution, kind of like a probability distribution. They have to sum up to 1. They are positive numbers, right? These quantities. Yeah. And what is the probability distribution which maximizes this weighted summation? The only way is all the probability you have to put it on lambda 1. Is that clear, Aditya?
Yes, sir.
Yeah. Okay. So hence, what have you proved? What have we managed to prove?
So that when we are finding the best fit one-dimensional subspace for a set of points,
yeah,
that the unit vector corresponding to that subspace, the basis for that will be the eigenvector for MM transpose normalized.
Yes. So V1 is also orthonormal eigenvector. So orthonormal, that means it is normalized, right?
Yes, sir.
Yeah. So we have proved this theorem. Okay. Everybody agrees. Yeah. So now we want to generalize this to arbitrary dimension. Yeah. So before we do that, yeah, I just want to quickly make one comment. Yeah. So we showed that this V1 is argmax, yeah, of norm V equal to 1, norm V equal to 1 m times V the whole squared. Yeah, this is something we showed. You agree?
Yes, sir.
Yes, sir.
Yes, sir.
Now my claim is, yeah, take V2 is nothing but argmax, yeah, of V which is perpendicular. Everybody understands what V1 perp is, no?
Yes, sir.
Do this argmax over V1 perpendicular, not the entire vector space. If you do that, you will get V2. Is the claim clear?
Yes, sir.
Yeah, so why is that true? How will you prove it?
By recursion.
Sir, it's the second greatest value and it's...
So it's the same argument since now we just are not allowed to pick V1.
Yes,
Yeah.
sir.
So let's take this here. Yeah. So we have argmax. Yeah.
Sir, shouldn't it be a norm of MV squared?
Yeah, sure. Thank you. Yeah. So this quantity will become this quantity eventually with V belonging to V1 perpendicular and norm V equal to 1 and summation over I equal to 1 to n lambda I Vi dot V. Okay, the squared. Okay, so what can we say about this?
We can't pick the first one. We can't pick V1, so we go for the next best value, which is lambda 2. And we know that it's perpendicular to V1, so we can just pick that instead. And using the same
Anyway,
argument as before.
Yeah. So anyway, V is perpendicular to V1 per. So the first term in the summation is 0. Yeah. The first term in summation is 0. So this is basically summing your 2 to n. Sorry, lambda I Vi dot V. Yeah. And when is this maximized? When is this maximized? V2 with value lambda 2. Everybody agrees?
Yes, sir.
Yeah. So in general, you can also imagine Vk is nothing but argmax, yeah, of V belonging to span of V1 to Vk minus 1. Yeah. Norm V perpendicular. Norm V has to be equal to 1. M times V the whole squared. Yeah. Same argument. Everybody sees the proof of this?
Yes, sir.
Okay, very nice. Yeah. Okay. So we have a nice way of representing eigenvectors. Yeah. So these are kind of some argmax thing going on. Yeah. So now let's try to prove the general case. Yeah, which is not general case. Let's try to prove that the best fit two-dimensional subspace. Yeah. So the claim is best fit two-dimensional subspace is equal to span of V1 comma V2. This is what you want to prove. Yeah. Okay. So how do we prove it? Any ideas? So let W W be the best fit two-dimensional subspace. W is the best fit two-dimensional subspace. Yeah. Now let's choose a basis for W. Okay. So a basis for W is W1 W2. So W1 comma W2 is orthonormal basis for W. Okay. W1 W2 is a orthonormal basis for W. Yeah. My claim is, so without loss of generality, the claim is we can choose W2 to be belonging to W1 perp. Can we do that?
So isn't it going to belong to the V1 perp anyway? Because it's
Why?
orthonormal.
Why?
Because they're orthonormal, isn't it?
But W1 W2 is the orthonormal basis for W. V1 to Vn is a orthonormal eigenvectors of some other matrix. Right? We want to show that W equal to span of V1 V2. Right now we don't know W equal to span of V1 V2. Right?
So it's not trivially true because we could have some other vectors instead of V1 and V2. So we'll have to prove that.
Yeah, we have to prove that. We have to prove that. I'm saying let W be the best fit subspace. Maybe it is not equal to this. W is the best fit subspace. Yeah, but and let W1, W2 be orthonormal basis for that two-dimensional subspace. Okay, but if you look at W1 perpendicular, yeah, W1 so remember, I mean your vector space V is a direct sum of W1, span of W1 and W1, sorry, span of V1, yeah, direct sum, span of V1 perpendicular. You agree?
Yes, sir.
Yeah. So, and your W is a two-dimensional subspace. W is a two-dimensional subspace. This implies, yeah, there exists, yeah, a vector where exists, let's say, yeah, this is W2 belonging to, yeah, W intersection V1 perp, yeah, such that W2 not equal to 0. Yeah. So W2 is a vector, yeah, which is orthogonal to V1 and also in W. It's a non-zero vector. Yeah. Why should such a vector exist? Because W is a two-dimensional subspace. Yeah, and V1 is also a one-dimensional subspace. Yeah, so this is only a one-dimensional subspace. This is a n-1 dimensional subspace. So there should exist a vector W2 which is belonging to V1 perp. Do you agree? Is that clear?
Yes, sir.
Yeah. So there exists a vector, yeah, which is in yeah, W, which is orthogonal to V1 perp. Yeah, I will choose that as my first basis vector, and I will choose W1 in W, which is orthogonal to W2. Yeah, and this forms a basis for W. Is that step clear?
Yes, sir. So, but just to confirm, W1 can belong to both span of V1 or span of V1 perp. That is not confirmed yet, right?
W1, yeah, W1 could belong to V1. Yeah, that is right. Yeah, W1 could belong to V1 perp also. Yeah, completely agree. Yeah, I'm just choosing W2 to be orthogonal to W1, sorry, V1, and choosing W1 to be orthogonal to W2, which inside W. Okay. Yeah. Now, yeah. So now, what is W1 and W2? Yeah. So W1 and W2, since it is the best fit subspace, yeah, it is the argmax of something. Yeah. If you take W1 and W2, such that these are, yeah, yeah, these are vectors with the norm equal to 1, which basically, remember, yeah, which maximizes what?
Norm of MV square.
Yeah, norm of, so there is two things here. So the norm of MW1 squared plus norm of MW2 squared. You agree?
Yes, sir.
Yeah. So this is basically the sum of squares of projections onto the vector space W, right? Sum of squares of projections onto W. Yeah. Right. Now, what can you say about this quantity and this particular quantity? Yeah, how does this relate to? So W1 and W2 is the argmax, which has the maximum sum of squares of projections. Yeah. which is minimizing the sum of squares of perpendicular distances. Yeah. Now, what can we say about this quantity and this quantity?
Sir, since W2 belongs to V1 per, we can say that W2 is definitely equal to V2, and that will imply that we can have W1 as V1.
Yeah, I think you are jumping 2 steps ahead. Yeah, we will get there. But from this expression, yeah, what can we say about these two quantities?
The left one is less than equal to the right one.
Yeah, because in this argmax, V1 and V2 was also considered. Yeah, so this W1 is perpendicular to W2 also. Okay, so one more condition is there. Yeah. In this argmax, yeah, V1 was V2 was also considered, but we chose W1 and W2. That means this is greater than this, right? Right? Is that clear?
Sir, could you repeat why the inequality exists?
So W1 and W2 is the argmax of this quantity, right?
Yes, sir.
So this is when this quantity is maximized. So V1, V2 was also a choice when you did that maximum, right?
Yes, sir.
Yeah. So the value for V1 has to be less than or equal to the value for W1, W2.
So I still don't understand, sorry.
So if I substitute V1 and V2, yeah, the value you get here should be less than the value for W1 and W2, no? W1 and W2 achieves the maximum for this. You agree?
Yes, sir.
Yeah. So if I substitute V1 and V2 here, the value should be lesser.
So we don't know anything about V1 and V2 at this point, or
No.
we've already taken that to be the.
No. We know that W1 and W2 is the maximum of this. That we know, right?
Okay, sir. Yes, sir.
Yeah, that's what I'm saying. W1 and W2 is the maximum. It is the best with subspace. So this has to be greater than this.
Yes, sir.
Yeah. Okay. Good. Yeah. So also one more thing we know. Yeah. So what do we know about V1 and W1?
Sir, may I ask a question?
Yes.
Sir, could I not separate the terms in the argmax, since W1 and W2 we know them to be perpendicular, so like orthogonal. So could we not say that argmax, like this whole expression is equal to argmax MW1 norm squared plus argmax MW2 norm squared, where in the first term I have W1's constraints and in the second term I have W2 constraints?
But W1 and W2 are related, no? I don't know. Maybe it is not.
Sir, did we not say W1 perp W2?
Yeah, sure, you can do that. Yeah.
So there's no component of W2 in W1 and vice versa. So sir, if we separate the argmaxes, then we can directly say that V1 and V2 are the answers for the individual argmaxes, right?
Yeah, beautiful. Yeah, that's much better. Okay. So what Shashwat is saying is, yeah, so the first term only depends upon W1, right? Yeah. So let's separate out the argmax, yeah, W1. But then okay, how do you, there's a problem now, how do you separate out this?
Sir, we said W1 perp W2 in the conditions there.
Yeah, but the thing is, when you separate out that argmax, we don't know what the maximum for the first part is. And W2 has to be perpendicular to that maximum, no?
Sir, can't we just equate W1 and V1, because they have to be the best in any case, and W2 and V2 have to depend on the W1 and V1 respectively, and then we can equate them.
Yeah. So V1 is the maximum of this, right? Everybody agrees with that.
Yes.
Yes, sir.
So everybody agrees that m times V1 squared, yeah, is greater than or equal to m times W1 squared.
Yes, sir.
Because V1 was the argmax.
Yes.
Yeah. Now remember, we chose V2 W2 to be perpendicular to V1. Yeah. We chose W2 to be perpendicular to V1. And what is this saying?
So
All
for
the
the whole
vectors perpendicular
space.
to V1, argmax is V2. Like V2 gives the argmax, right?
Yeah.
Yes, sir. So we can write the same in equation for V2 and W2.
Yes.
Everybody agrees?
Yes, sir.
What do we have here with along with equation 1?
So we just added and formed an equative.
Yeah, so yeah. And what does that mean about this argmax?
That it's max when W1 equals V1 equals V2. Like.
Yeah, so what this says is V1, V2 was another solution of the argmax. Right? Okay, maybe W1, W2 is a solution, but my V1, V2 is equally good as W1, W2.
But
Yes,
sir, because it's argmax, wouldn't the solution be unique?
No, no need. Why should be unique?
And sir,
Understood.
Sir, did we not consider, like, in this expression, are we not looking at W1 and W2 as variables?
No, no. So W1 and so let me call this W1 star and W2 star inside the argmax. Okay, that avoids a lot of confusion. Yeah. Yeah. Can you agree that V1, V2 is also a solution to the argmax?
Yes, sir.
Yes, sir.
Yeah. So what have you shown? Have you proved the claim?
Yes, sir.
Yes, sir.
So this is the claim we were proving initially. Best fit two-dimensional subspace is span of V1, V2. Yeah. So V1, V2, if you have a subspace which is W1 spanned by W1, W2, then V1, V2 is equally good as that particular thing. So you could, V1, V2 is one of the best fit two-dimensional subspaces, which is as equally good as
So
any
here
other.
also we can say that now that if the eigenvalues are distinct, then V1, V2 are the only solutions here.
Yes.
For argmax.
Yeah, the thing is, if V1 is a solution, minus V1 is also a solution. You can.
So any orthonormal basis for that subspace would be a valid solution.
Yeah, that is right. Yeah, any orthonormal, any orthonormal basis for that this span of V1, V2 will be also be a solution. That is right. Yeah, so you can.
So what is the symbol you used between this norm W1 star and norm W2 star equal
this
to
one?
No, below. Like in the condition, second condition.
This is
Below
orthogonal. They are orthogonal.
No, above this.
Orthogonal. Oh, this is comma. This is just comma. I meant. Okay. Sorry. Yeah. Yeah. This I just meant comma only. My erasers are too big and I cannot always. I don't know. I cannot erase it for some reason.
Yes,
yeah, please.
I didn't want to interrupt.
Yeah,
So I
please.
didn't get the logic of choosing W2 to be in V1 perpendicular.
Yeah. So why did we choose this? This allowed us to make this argument. This allowed us to make this argument. Yeah. Why is this true? This is true because we could write V2 like this. V2 is all vectors, argmax over all vectors orthogonal to V1. So if W2 was orthogonal to V1, we could make this argument. Yeah, that's a good question. Yeah. Okay. So yeah, so we have proved for 2 dimensions. Yeah. So how do you prove the general case? Any suggestions?
Extend this to K.
Sir, can we use the separation argument for the general case with k vectors? Because assuming that w1 star per w2 star dot per wk star,
Yeah.
and with every term I reduce the dimension of the space by getting rid of one vector from the basis, so on and so forth, and then I maximize for each of the subspaces.
Yeah. So you need to make use of this definition. Yeah. And again, you will choose. Yeah. I mean. So the easier proof is actually by induction. Okay. Induction is always the best way. Okay. So we already know the base case. Yeah. So by induction. Base case we know. Yeah. So base case. What is base case? Best fit one dimension is best fit one dimension is span of V1. This we know already. Yeah. And inductive case, what do we need to prove? Assume that the best fit, yeah, k minus 1 dimension equal to span of V1 to Vk minus 1. Yeah. This implies that the best fit k dimension equal to span of V1 to Vk. You agree? This is what we need to prove.
Yes.
Yes, sir.
Yeah. And yeah, I mean, today our time is over. Yeah. And the argument is again going to be the same. Yeah. We just need to make use of this definition of Vk. Yeah. And also here it will be W1 to Wk and argmax of such that norm equal to 1, all of them has to be perpendicular. Yeah. Just make use of this definition and this. Yeah. Just as we argued for this 2-dimensional case, we can also make this argument.
So you also have to choose W3 so that it belongs to V1 comma V2 per and so on.
Yeah. So you will choose a Wk belong to span of V1 to Vk minus 1 perpendicular. Yeah. You will choose Wk to be this belonging to span of V1 to Vk minus 1 perpendicular, and then it will get you the argument. Okay. Yeah, I suggest that yeah, you try it yourself. Okay, I mean, it's there in the textbook. I have given the reference. Yeah, and yeah, I mean it's the same argument. Yeah. So what did we do? I will just close this quickly and take questions. Yeah. So we wanted to prove that Svd is the best fit subspace. Yeah. And best fit means sum of perpendicular distances, squares of perpendicular distances is minimized. But we said that is same as maximizing the sum of projections. So that is the same as maximizing the sum of projections. Yeah. And yeah, and there was a very concise way you can write the sum of squares of projections, which is m times v the whole square. Okay, and we also we first proved that yeah, for k equal to 1, V1 span of V1 is the best fit one-dimensional subspace. Yeah, all we did was we just do some manipulations and use the fact that V1 is the eigenvector of M transpose M, and we observed that we use the spectral decomposition, yeah, spectral decomposition, and yeah, we just observed that this summation is maximized when V equal to V1. Okay, and okay, and we also made a general argument that so V1 is argmax of this quantity and V2 is argmax of this quantity, and in general Vk is argmax of this quantity. Yeah, so we had another characterization for these eigenvectors. Yeah. And finally, we also showed that the best with two-dimensional subspace is span of V1, V2. Yeah. How did we do that? Let we assume that let W be the best with subspace. Yeah. We could choose a orthonormal basis for W such that W2 is perpendicular to V1. Yeah, because this is a two-dimensional subspace and V1 is only a one-dimensional thing. Yeah, one-dimensional subspace. So yeah, there exists a V2, W2 which is belonging to W1 per, and we choose W1 to be orthogonal to W2. So since it is the best with two-dimensional subspace, W1, W2 maximizes this quantity. Yeah. So in particular, for maximizing this, V1 and V2 was also a choice. So we got this equation. Yeah. So this was the argmax, that is this less than or equal to. But then we observed that when we choose V1 as the best fit line, W1 was also a choice. So this was the argmax. So this has to be true. And when we chose W2, yeah, when we chose V2 to be the argmax here, yeah, orthogonal to V1, W2 was also a choice. So this inequality is also holding. But then now you have that inequalities both ways, so these two has to be equal, which implies that V1, V2 also is a best fit two-dimensional subspace. And the same argument can be generalized to induction to prove the general case. Is that fine?
Yes, sir.
Okay. Okay, I can take questions. That's all for the lecture today.
So I had one doubt. So we've assumed that this is over the real space, right? Because I think on page 3, yeah, this one, we did like V transpose Vi transpose V is equal to Vi comma V squared. So we're making the assumption that VIV is equal to VVI, right?
So what is VVI? Like, what kind of object is that? Vi transpose V.
That's dot product, right? So, but we've assumed that V transpose Vi is equal to Vi transpose V. So that only holds true in the real space, right?
Yes, yes. Yeah, we already said this thing is actually the dot product we are meaning.
Okay.
Yeah. So we are not saying with respect to any general inner product.
Yeah.
And I am just using this notation because this dot is very small and invisible. Yeah.
Okay.
So that
to
emphasize that I am just using this notation.
Okay, makes sense. Thank you.
So will you be taking the session today for solving the questions from that previous assignment, sir? The graph ones, especially the bipolar graph question.
Yeah, yeah. So I have a tight schedule actually today. Yeah. Either I will be doing it today or I will be doing it in Saturday's class. Okay. Yeah. So our office hours is scheduled at 3:30, and many of you said they have a problem with 3:30. Yeah. So I will try to be available at 5. Okay.
So we have a DSA quiz from 5 to 6 today.
Yeah. So after 6, I have some trouble. So yeah. So okay. Let's meet at 6 then. Okay. Let's meet at 6. Yeah. So I'll be putting out a message at 6, and yeah, we can meet in the course Teams. I will send out a link.
Thank you, sir.
Yeah.
Okay, thank you, sir.
Any other
Thank you,
questions?
sir.
Yeah.
Thank you, sir.
Thank you. Bye for now.